Today we are going to be talking about a few different types of gas laws, and we'll be starting right now with something called Boyle's law. So for Boyle's law, I went ahead and put a diagram here to show these gases, which I represented by these little blue dots, in two different containers, and we're going to discuss what those mean. So in the container on the left, notice we have this plunger at the top and it's not pushed down very far, so that volume is still relatively large or high. Because that volume is high, notice that those gas molecules have plenty of room to move around. They're still going to be bouncing off of each other and off of the walls of this container from time to time, but it will not be too frequently. So we can say that the pressure is low while the volume is high. Now, if you look on the right-hand side, we have pushed that plunger down in the container to decrease that volume. As we've done that, we have the same number of molecules, but they're so much closer together. Those gas molecules have much less room to move around. Because of that, they will be bouncing off of each other, off of the walls of the container far more frequently, which means our pressure is high compared to the diagram we had on the left, while the volume is relatively low. So as that pressure increased, the volume decreased. Or you can say as the volume increased, the pressure decreased. Notice that as one is going up, the other is going down, or as one is going down, the other is going up. What that tells us is that pressure and volume are inversely related. So let's look what we do now. We can take that idea and put it into an equation. Notice we have this equation right here. This is Boyle's law. It is the official equation. This tells us that the pressure in the first container times the volume in the first container is equal to the pressure in the second container times the volume in the second container. So if you change one of those values, if you increase the pressure, the volume should go down. If you decrease the pressure, the volume should go up, and vice versa. In this case, pressure is measured in ATM. ATM just means atmospheres. And I went ahead and wrote out our conversion here. You have 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 101.3 kilopascals. So you don't have to memorize this conversion. It's provided for you on your reference sheet, but I just wanted to put it here as a reminder. If you are given your pressure in anything other than atmospheres, you will need to convert it to get your final answer. And then volume is measured in liters, which we should be used to by now. So let's apply this to an example problem. We have here that at 1.7 atmospheres, a sample of gas takes up 4.25 liters. If the pressure on the gas is increased to 2.40 atmospheres, what will the new volume be? So I went ahead and pulled out our variables and labeled them. So P1, V1, and P2 is what we are given. So we are solving for V2. We want to find that new volume. We should notice that we are increasing our pressure from 1.70 to 2.4. So that tells us that our volume should be going down. So as pressure increases, volume should decrease. And we can confirm that when we look at our final answer. So I have our equation right here that we just gave you. P1 times V1 is equal to P2 times V2. I went ahead and divided both sides by P2 so that I'm left with V2 by itself. So V2 is going to be equal to P1 times V1 over P2. I can go ahead and plug in my values now. I don't have to convert anything because they're already in atmospheres and liters. And notice that atmospheres will cancel out since there's on the top and the bottom. And we are left with V2, which is equal to 3.01 liters. As I mentioned before, because we are increasing that pressure, the volume should go down. We said that our second volume is 3.01 liters, and the initial is 4.25. So it did go down just like we predicted.